Microcontrollers are everywhere. They are tiny computers found in everyday objects. Your microwave, TV remote, and even your car use them. These tiny chips contain a processor, memory, and input-output pins. The I/O pins are the connections to the outside world. Think of them as the microcontroller's senses and muscles. They allow the microcontroller to interact with its environment. These pins are crucial for controlling motors, reading sensor data, and much more. Microcontrollers use two types of signals, analog and digital. Analog signals are continuous and can have any value within a range. Think of a dimmer switch. You can gradually adjust the brightness. Digital signals are discrete, meaning they can only be one of two states, high or low. A light switch is a good example. It's either on or off, with no in-between. Microcontrollers need both analog and digital pins to interact with the real world effectively. Digital pins are perfect for controlling devices with on-off states, like LEDs, motors, and buttons. Analog pins, on the other hand, are essential for reading data from sensors that produce continuous values. These sensors might measure temperature, light intensity, or position, providing information that requires a range of values. Early microcontrollers primarily used digital pins. These pins interfaced with simple switches and LEDs, enabling basic control tasks. As technology advanced, the need for more complex interactions arose. This led to the development of analog pins, allowing microcontrollers to interpret data from analog sensors and control devices, requiring varying outputs. Section 5. Visualizing the difference, analog versus digital signals and pins. Imagine a graph. On the x-axis we have time, and on the y-axis we have the signal strength. An analog signal would look like a continuous wave, smoothly transitioning between different values over time. A digital signal, however, would appear as a square wave, abruptly switching between high and low states. Microcontroller pins are designed to handle these specific signals. Analog pins are marked A, followed by a number, like A0, A1, etc. Digital pins are usually numbered, such as 0, 1, 2, and so on. Section 6. Analog in action, real-world applications. Analog pins are essential in applications requiring precise measurements or variable control. For instance, in a thermostat, an analog temperature sensor provides continuous temperature readings. The microcontroller then uses this data to adjust the heating or cooling system accordingly. Another example is a light dimmer. The microcontroller uses an analog output to adjust the brightness of the light bulb smoothly. Section 7. Digital dominance, applications of digital pins. Digital pins are incredibly versatile and widely used in various applications. In a simple example, a button connected to a digital pin can trigger an action, like turning on an LED. In more complex systems, digital pins control motors, relays, and even communicate with other devices using protocols like SPI and I2C. Section 8. Sensing the world, analog and digital sensors. Sensors are the eyes and ears of a microcontroller, providing information about the environment. Analog sensors like temperature sensors, light sensors, and potentiometers generate continuous analog signals. Digital sensors, such as ultrasonic distance sensors, Hall effect sensors, and button switches, produce discrete digital signals. Section 9. Mastering microcontrollers. The importance of understanding pins. Understanding the difference between analog and digital pins is crucial for successfully working with microcontrollers. By selecting the appropriate pins and configuring them correctly, you can unlock the full potential of these versatile devices. Whether you're building a simple LED circuit or a complex robotics project, knowing how to utilize analog and digital pins effectively will be the key to your success.